Hello students, hope all are doing good. In the last class we have studied about the introduction part of the first exercise. So now we are going to solve the problems which is given in 1.1. So the first problem is use Euclid's division algorithm to find the HCF of 135 and 225. So already I have taught you by using the example problem. Now we will solve it. Now find the solution. Since 225 is greater than 135, consider 225 as A and 135 as B. So according to the equation, what is that equation? That is B into Q plus R, right? So consider A equals 225 and consider B as 135. Now try to solve, try to find Q and R. So you can only divide once, 135 ones are, and the remainder is 225 minus 135 is 5 minus 5 is 0, then 2 minus 3 is not possible, take one borrow, then 12 minus 3 is 9. So R is 90. Now consider 135 as A and 90 as B. 90 also you can solve only once. So the remainder is 45. 135 minus 90 is 45. Now consider 90 as A and 45 as B. So 45 into 2s are. So you will get 90, remainder you will get is 0. So therefore HCF of 135 and 225 is, see in which step you will get remainder as a 0, that in that step B you should consider as the HCF of those two number. Clear? Now let's move to the second one. See the second problem, 196 and 38,220. So here in this case, solution 38,220 is greater than 196. Here if you find the solution by using the Euclid's division algorithm in step by step, it will be very lengthy. So what we can do, try to divide the given number as it contains more digits. So try to divide this one. How much you will get? So 196 into 2, 2 6 are 12, 1 19. So you cannot consider 2s, so you can directly consider as 1s. So 196. Now subtract this one. 6 minus 2 not possible, take one borrow. 12 minus 6 is 6. So here you have 7. Then 7 minus 9 again not possible, take one borrow, it will become 17. 17 minus 9 is 8. Then here you have 2. 2 minus 1 is 1. So here we have 186 and 196. So this value is less than 196. So bring 2 down. Now think, it is almost, if you consider 196 into 10s, it is very near, right? Like 1900 something it will come. So try to consider 196 into 9. So 9 5s are 45, 9 6 are 54, fine. 81 plus 5 86, then 8, 9 1s are 9 plus 8 is 17. So you can consider 196 into 9, so that is 1764. Now subtract this one. So 2 minus 4 is not possible, take one borrow, it will become 12. 12 minus 4 is 8. So here you have 5. 5 minus 6 is not possible, take one borrow, it will become 15. 15 minus 6 is 9. So here you have 7 after taking borrow. 7 minus 7 is 0 and 1 minus 1 is 0. So here you have 0, so bring down. So here it is 0, maybe you can consider 196 into 5. 5 6 are 30, 3 carry, then 9 5 are 45 plus 3 8, 4 carry, 5 1s are 5, 9. So 196 5 is 980. So the answer you will get is 0. So according to this Euclid division algorithm, directly you can write it as 38,220 equals 196 into 195. This is Q, right? This is R. So R you will get is 0. So this is how you can solve the given problem if it is having more digits like 5, 6, 7 like that. So in this step only you got 0, right? So this 196 is itself a HCF of given two number. Therefore HCF of 38,220 and 196 is 196. Now consider the third problem. 867 and 255. 867 and 255. Now since 867 is greater than 255, consider 867 as A and 255 as B. Now how to solve this one? So 204 is 800, so it will become so not possible. You can consider into 3. If you consider into 3, how much you will get? 3 5s are 15, 5 1 carry, 3 5s are 15, 16, 1 carry, 3 2s are 6 1 7. So this one you can consider. So 867 minus 765, what you will get? 7 minus 5 is 2, 0 1, 102 you will get. So the remainder will be 102. Now consider (255) as A and 102 as B. So into 2 you can consider, that is 2 2s are 4, 2 0s are 0, 2 2s are 2 1s are 2. So 255 minus 204 you will get is 51. So remainder is 51. Now consider 102 as A and 51 as B. Obviously 51 into 2 is a 102, remainder is 0. So 51 is the HCF of the given two number. Therefore HCF of 867 and 225 is 51. Now let's move to the third one. Second problem is, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. So according to the question we can consider, let A be any odd integer and B equals 6, right? So if B equals 6, R can take the value of 0, 1, 2, 3, 4, 5 because R is greater than or equal to 0 and less than equal to 6, not equal to 6. That's why we consider only the values till 5. Always the R value should be less than 6, not equal to 6. Now by Euclid's algorithm, now substitute the value of R in the given in the Euclid's equation, that is A equals BQ plus R. This is the standard equation where R is greater than 0 and less than B. So consider B equals 6 and R equals all these value. So first one, if you consider R equals 0, so A will take the value of 6q plus 0, it will become 6q. This is what? Even. If you substitute any value to q, like 1, 2, 3, 4, 5, it will give your even number only. Now consider r equals 1. A equals 6q plus 1. This is odd. Why it is odd? Because substitute any one value to q. Substitute 5. 6 into 5 plus 1. 6 5s are 30 plus 1 equals 31. 31 is a odd number, right? So that's why we consider it as an odd number. Now consider r equals 2. A equals 6q plus 2, and this is even number, even integer. So r equals 3, a equals 6q plus 3, this is odd integer. R equals 4, a equals 6q plus 4, this is even integer. R equals 5, that is a equals 6q plus 5, this is odd integer. So see, here you have odd integer, here you have odd integer, and here you have odd integer. So a can take the form of 6q plus 1, 6 3 plus 1, 6q plus 5 when it is odd integer. Clear? So you can write, therefore, any odd integer can take the form 6q plus 1, 6q plus 3, 6q plus 5. Clear? Now let's move to third one. Third problem is, an army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of column. What is the maximum number of column in which they can march? So what is the question here? See, there are total 161 members of army group, and they have to parade along with the 32 members. Okay, so here we have a two group of 32 and 616 members. So we have to find out how many number of columns we need. Okay, so this 616 members, they can march along with 32 members. So we have to find out how many number of columns is required. For that, find the HCF of these two number, you will get the number of columns. So since 616 is greater than 32, consider this as A and this as B. So 616 equals 32 into, so how much you can consider? You can almost double the 300, right? So 32 into 10, so 20 you cannot consider, it will become 640, right? So 19 you can consider. So if you consider 32 into 19, so remainder you will get is 8. Now consider 32 as A and 8 as B. So 8 into 8 4s are 32, right? And remainder is 0. So 8 column. So 8 is the HCF of these two numbers. Therefore HCF of 616 and 32 is 8. So they can march in 8 columns. Fourth problem is, use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Okay, we did this problem in example problem, or now we'll see how to solve this one. Consider let A be any positive integer and b equals 3. So if b equals 3, r can take the value of 0, 1 and 2 because r is greater than 0 and less than 3, right? So now consider Euclid's division. Use Euclid's algorithm that is a equals bq plus r, where r is greater than 0 and less than b. Now substitute b equals 3 and r equals 0, so you will get 3q, and substitute r equals 1 and substitute r equals 2. So you will get 3q plus 1 and 3q plus 2. See, by seeing this, it is in the form of 3m and 3m plus 1 and 3m plus 2. Therefore, the square of, you have to square it out. Now after considering this, square this one, square on both the side. What you will get, a square equals 3q whole square. You will get 3 3 is a 9, 9q square, and we have to show it in the form of 3m, right? Take 3 as common. 3 3 is a 9q square. So where m equals 3q square. Now consider another one, that is a equals 3q plus 1. Here also square on both the side. What will happen? A square plus 3q plus 1 whole square. Now expand in the form of a plus b whole square. Now expand it. A square equals 3q whole square plus 1 square plus 2 into 3q into 1. So you will get is 3 3 is a 9q square plus 2 3 is a 6q plus 1. So here take 3 as common. 3 3 is a 9q square plus 3 2 is a 6q plus 1. See, this is in the form of 3m plus 1, where m equals 3q square plus 2q. You can consider a square equals 3q plus 2 whole square, and you can solve it. Okay, so the square of any positive integer is either of the form 3m. See, this is 3m and this is 3m plus 1. So at the end you can write, therefore the square of any positive integer can take the form 3m and 3m plus 1. This is how you have to solve it. Already we did this kind of problem in example problem. As an example problem we already solved it. Now let's move to the fifth one. Fifth problem is use Euclid's division lemma to show that here they are asking cube of any positive integer is either of the form 9m plus 1 and 9m plus 8. So here what you have to do, you have to consider a equals 9m, okay, not 3m, and b equals 9. Clear? So whichever they given, consider that and do it. Don't do for all the values of 0 1 2 3 4 5 6 7 8. Only do it for 0 1 and 8. Clear? So try to solve this one. Here you have to cube, like a cube, and if it is in 9 cube plus 1, you have to expand it. So here you have to consider 3m only or 3q only, then you have to show it in the form of 9m. Clear? Now try to solve this one. Solution: let a be any positive integer and b equals 9, or you can consider 3. When we cube, you will get 9m. So do it first one. A equals 3m. Now here they given m, no, consider m only, so you won't get confused at all. So if you want, you can consider q also, that's fine. So here what we have to do, we have to do cube on both the side. Now cube it on both the side. A cube equals 3m whole cube, or you can consider q 3q whole cube. So 3 3 is a 9, 9 3 is a 27, q cube, right? So how we have to represent this one in the form of 9m. So 9 take as a common. 9 3 is a 27 equal 3. So this is 9m, where m equals 3q cube. Clear? Like this you do it for 3q plus 1 whole cube. Then a cube equals 3q plus 8 whole cube. So expand this one in the form of a plus b whole cube identity. You will get the answer. Take this one as a homework. I hope you understood all the problems of today's class. If you have any doubt, please write it in the comment section. Thank you for watching my video. If you are new to my channel, please subscribe it. See you in the next class. Bye bye. Take care.